Welcome back, everyone. Let's jump right into the structural layout of massive 6th and 7th generation drill ships, like the GF-12000. I want you to picture an X-ray view of this absolute beast of a vessel for a second. It's out there in deep, unforgiving oceans, carrying thousands of tons of heavy steel, fuel, and equipment. By all logic, this hull needs to be completely solid, right? Like as watertight as humanly possible. But right in the dead center, there's this gaping structural anomaly. Just a massive, intentional hole cut straight through the hull. So how on earth does a drill ship like the GF-12000 stay afloat, let alone safely drill a well despite this?
Well, to figure that out, we have to look at what that opening actually is. It's called the moon pool, and I love how one seasoned offshore engineer in our sources described it. They said, stepping into this space feels like walking into a cathedral to engineering. It's an incredibly evocative thought, right? Because this isn't just some empty void, it is literally the sheltered central nervous system of the drill ship. This is the exact spot where massive equipment like the blowout preventers, the BOPs, and thousands of feet of marine riser are assembled and then deployed straight down to the seabed.
And to truly appreciate why this is such a marvel, you've kind of got to grasp the sheer physical dimensions we're talking about here. The GF-12000's moon pool measures roughly 24.8 meters long by 12.8 meters wide. Now, doing the math, that translates to an opening of approximately 317 square meters right in the middle of the ship. Take a second to visualize that. You're essentially looking at an open hole with the base footprint of a small apartment building cut directly through the vessel.
Which brings us to the ultimate, totally counterintuitive question. There's a massive hole in the ship, so why doesn't it sink? It's the ultimate structural Trojan horse. You see, the moon pool is arguably the single riskiest piece of structural engineering on the entire vessel. You've got this massive opening totally exposed to the sea with a live, high-pressure well directly underneath it. If this isn't engineered flawlessly, it is an absolute disaster waiting to happen.
Section 1. A ship within a ship. Okay, let's dive into this.
So how do naval architects actually solve this massive problem? Well, the GF-12000 is basically built like a set of Russian nesting dolls. Think of it as a tank within a tank. If this drill ship just had a single skin and a single bottom, which, is how many older or different types of vessels are built, one grounding event or a single collision could instantly flood the entire vessel. But with a double bottom and double side shell arrangement, the outer hull faces the ocean, while an entirely separate sealed inner hull protects the vessel's critical spaces. If the outer shell is breached, the inner shell is right there to act as a shield. It keeps the vessel completely watertight. Plus, it gives operators a way to control the ship's trim and heel using precise ballast distribution within that safe space.
So, the absolutely crucial concept here is redundancy. Classification societies like ABS and DNV strictly mandate this double hull redundancy for any vessel of this size and purpose. But they actually go a step further. The void space between that inner and outer shell, it isn't just one big empty pocket. It's subdivided into multiple separate water ballast tanks that run the full length of the drilling zone. This means if one tank gets punctured, the flooding is completely contained to just that single compartment. That prevents the ship from losing overall stability and, critically, buys the crew time to react.
Section 2. The complication. Moon pool resonance.
Now, solving the hull breach problem is great, but it introduces a completely different, massive physics problem. Because the moon pool is open to the ocean below, you now have a 317 square meter column of seawater sitting right inside the hull, and it is in constant motion. To mentally picture what's happening here, ask yourself, have you ever opened a car's sunroof at highway speed? You know that violent, rhythmic buffeting of air that hurts your ears and shakes the whole cabin? But then you close it a little bit or change your speed, and it suddenly stops. The moon pool acts exactly the same way, except instead of air buffeting your car, it's thousands of tons of seawater resonating inside a giant steel shaft.
In marine engineering, this phenomenon is known as piston mode sloshing. It's basically the tendency of the water trapped in that vertical shaft to surge upward and downward violently when the vessel moves at certain frequencies. Without mitigation, this uncontrolled resonant column of seawater punches upward with incredible force. It actually amplifies the vertical water movement well beyond whatever the actual ambient wave height is outside the ship. To help prevent this from getting out of hand, operators actually have to carefully manage the ship's forward speed and heading during transit just to avoid hitting those specific resonant frequencies.
And that leads to a cascade of physical consequences known as the free surface penalty. Basically, the larger the open water surface inside the hull, the more it reduces the vessel's effective metacentric height, or GM. In plain English, It imposes a severe stability penalty. But structurally, it's even worse. Think about this from a naval architect's point of view. If you removed your mitigations entirely, what's the first system that would be destroyed? Well, if that piston mode sloshing is left unchecked, that surging water would slam directly into the highly sensitive riser tensioning equipment located just above the moon pool. It would literally jerk and destroy the exact equipment that's meant to hold the drill string steady. No way you can let that happen.
Section 3. The fix: wave damping plates.
So how do you actually fix this buffeting sunroof problem on a multi-billion-dollar drill ship? Like we said, you can't just drill through a solid hull, so the opening has to be highly engineered. The solution? Wave damping plates. And this brilliantly illustrates the fix. These plates are engineered permanently into the hull inside the moon pool shaft, and they act exactly like baffles inside a liquid fuel tank. They break up the resonant water movement, they dissipate all that energy, and they protect the sensitive riser and blowout preventer equipment above from getting repeatedly slammed by thousands of tons of angry water.
To engineer this correctly, naval architects have to calculate the exact free surface area. By taking our length of 24.8 meters and multiplying by the width of 12.8 meters, they arrive at that 317 square meter plan area. They have to do this because they absolutely must mathematically account for that massive stability penalty in their operating margins. Every single calculation about the ship's center of gravity and buoyancy relies on knowing exactly how much that free surface of water is going to fight against the hull. It ensures the damping systems are sized perfectly to handle it.
What you should really take away from this explainer is that the moon pool isn't just a hole. It's a highly tuned structural feature. The double bottom, the double side redundancy, the exact dimensions, and those crucial wave damping plates all work together in a very delicate balance. If you get any part of this wrong, the ship either risks sinking from a single collision or literally ripping its own drilling equipment apart from internal water resonance.
But, this leaves us with a really fascinating paradox to set up our next topic. We just spent this entire explainer talking about how hollowed out the center of this vessel is, and how much volume is taken up by empty void spaces and ballast tanks just to keep it safe. So, how on earth does a ship with so much intentionally empty space manage to physically support up to 22,000 metric tons of heavy steel, drill pipe, and equipment on its deck? Well, that is exactly what we're going to uncover in our next explainer on variable deck load, or VDL. See you there.